What's up, guys? We're here for the Homework 8 introduction video, and Homework 8, I dropped my pencil, covers left-leaning red-black trees and 2-3 trees. And so if you haven't already watched the lecture covering these topics, I recommend it, but we'll do a quick sort of recap of how these structures work. First, an overview of the homework assignment itself. This assignment is just about coding up a left-leaning red-black tree, or LLRB. And so along the way, we're going to remind you that there is this cool analogy between LLRBs and 2-3 trees, but you're not actually going to have to write code for a 2-3 tree. And that's sort of, I think, like the point of an LLRB to an extent, right? Is we talked in lecture first about how, 2-3 trees are so awesome because they're balanced and they're like, you're going to get better runtime when you have a balanced structure. However, in practice, 2-3 trees are actually really, really hard to code. And so that's sort of why we came up with this red-black tree, is because it lets us like mimic the properties of a 2-3 tree while still being, at the end of the day, just a binary search tree that's easier to use than like a complicated B tree with like nodes with differing amounts of elements, basically. And so you can feel grateful and lucky today that we're just having you code the LLRB and not the 2-3 tree. You're welcome. And so in this homework, you're just gonna have to do the following methods: rotate left, rotate right, color flip, and insert. And in a way, all of these are really just helper methods for insert and other methods. But you're just gonna have to do insert. You don't have to worry about like removal from this red-black tree. And so, yeah, this is what we're gonna talk about. So you're going to recall that 2-3 trees and LLRBs are analogous, whatever. And the basic premise is that if you have a 2-3 tree that looks like what you have on the left here, the way we represent that is we just have a plain old binary search tree with one element per node like normal, but nodes with 2 elements are going to be represented by a red like symbolic node, and then the plain old black node. And so we can see that in these nodes with more than one element or 2 elements, the left item is shown to be a left red child of the other item in the node. And so we can see this was one node, right, in the 2-3 tree. This was one node, and this was one node. And what we have here is that the red nodes are left children of the other node they were like roommates with, I guess, is the way you can put it. And because we always make them the left child, we call this a left-leaning red-black tree, right? And so this is as opposed to doing something like GV. Oh, that was a horrible, okay, it can be neater. GV, right? Where you have this like right red child. We're going to put it on the left. And so by doing this and being consistent about it, what we end up with is a left-leaning red-black tree. So as we just saw, every single LLRB has a 1-to-1 correspondence with the 2-3 tree, which is really cool. But the thing is, this is easier than a 2-3 tree because all the nodes are essentially the same, they just have one element, and it's just like working with the regular binary search tree. And so we insert very similarly how we insert in a regular binary search tree. But of course, this is better than the plain old binary search tree because it's balanced. Because we're going to force it to have this correspondence to a 2-3 tree, we know that the tree is balanced with respect to the number of like black nodes that it has on a path. And so the way we maintain this balance or force the correspondence between our LLRB and our 2-3 tree is going to be through a series of rotations and color flips. So again, we have LLRBs. We want them to correspond to 2-3 trees to maintain balance. But this means that in order to keep the balance, we have to fix up our tree regularly. And so rotations are one of the tools we use to fix. And so the first one we'll look at is rotate right. Rotate right on a given node says, if let's say we call rotate right on T, we're going to take B as the left child of T, and we will make T the new right child of B. In other words, rotating right on a node takes that node and now makes it the right child of what used to be its left child. And so we can see what's going to essentially happen here is we're doing this sort of clockwise or right rotation. And so what we end up with is we have now the basic structure B, T, A, Y, W. And so what happened again was that B was the left child of T, and we made T the new right child of B. And we end up with something like this. And so B should now become the same color that T was, right? So in other words, the new root or the new parent is going to take on the color of T. So that was black. So B will be black here. And T should be colored red. And let's not forget that previously W and A were red. So those are going to maintain their color because they weren't really involved or affected by this rotation. And so this is the result, right? I want to note something important, which is that if, let's say, somehow B had a child here, right? Like, let's say there's C here, what would happen to that child? Because we imagine, again, each node can only have 2 children. C used to be B's child, but now B's hands are full in this new scenario, right? Like B can't hold on to C. And so where could C go? Well, naturally, if T used to have a left child that was B, and now T's hand is free, T can grab onto C. And of course, this doesn't break our binary search tree property, right? Because we can see that C is greater than B, so it's to the right of B, but it's less than T, so it's to the left of T. And so this works. And so again, the process for rotating right is we're going to say, oops, oh, what just happened? Technical difficulties. Anyway, if we call rotate right on a node T, we're going to take its left child, we're going to make T the right child of that node. And then we're also going to make sure that if that node had previously had a different right child, that becomes the left child of T. So that's the process here. Rotating left is pretty much the same, right? But we flip every time we're talking about left and right. And so again, let's say we call rotate left on T here. What we're going to do is take the right child of T, and now we're going to make T the left child of that one. And so again, we see this sort of rotation in this direction or a counterclockwise, like leftward rotation. And what we end up with is something like this, right? And so now the question again is, where does the W go, right? Because W used to be Y's left child, but now Y's hands are kind of full, right? It is the new parent of T. And so T adopts W, we can say, right? And so this is the structure we have. And then let me just go through and make all the colors correct. So again, Y should become the same color that T was. We see that in this example, T was black, so Y will remain black. And then also T should be colored red. And so now we end up with something like this. And so through rotations, we will see later exactly how these help us to do insertion. And if you are a little confused about like how this is working or why this works, I really, really recommend taking both of, like, take this tree, convert it to a 2-3 tree, and do the insertion on that and see how it compares and is like analogous to this. I think that is so helpful when we're talking about LLRBs, is to always bring it back to the 2-3 tree when you're confused. Because I do think at the end of the day, like, it's weird, LLRBs are easier to code, but 2-3 trees are easier to think about. And so being able to work with both and convert is really important. So those are rotations: rotate right, rotate left. We'll see how we can use those later. And then lastly, we want to talk about color flip. And so color flip says, if we flip the node Y, we're going to flip the color. And so again, we're assuming red and black. We'll flip between these. Are you guys seeing the order in which I wrote that? That's crazy. As well as both of its children. And so in this example, if we called color flip on Y, what we would end up with is that Y now becomes red because it used to be black, right? And then both of its children become black because they used to be red. And this is that. So those are the three main operations you have to do that will be helpful for the big kahuna, which is insert. And so insertion into an LLRB follows some basic steps. First, we do normal binary search tree insertion, right? So that means you start at the root and you go left or right based off if the value is less or greater than. You keep comparing, and then you eventually insert at a leaf, right? The thing is, the new node that you insert must be red. And so you're going to do normal binary search tree insertion. You put in a new red node, and then afterwards, you have to do some fix-ups as necessary to restore the LLRB properties. And so this includes rotations, color flips, and making sure the root is always black. Making sure the root is always black is just like a property of the LLRB. And if, again, you're confused about this, like when we go through these examples, I would recommend looking at 2-3 tree comparisons. So let's talk a little bit about the different cases for insertion. First, we'll start with the simple case. Let's say we wanted to insert the node R. And so here, doing normal binary tree insertion, we would say R is less than V, right? I have to maybe Q, R, S, T, U, V. So yeah, R is first, R is less, so we go left, right? R is greater than G alphabetically, so we go right. And then R is less than S, right? Q, R, S, T, U, V. So we go left, and now we're at a leaf, and so we can insert R. And again, we said we always insert as a red node. And so in this scenario, we see this was simple because when we're inserting, right, S is standing there and going, oh, I need to have a new child. We see it just has a red node as its left child. And so this is correct, right? There's no fix-up necessary because what we have is a left-leaning red-black tree, right? The left child is red. So this is totally fine. There's no fix-up necessary. And this is the end result. Now, what about this case? Let's say we want to insert T. So again, we would start at V. T comes before V, right? After G, and after S, right? So again, we're doing this like less than, greater than comparison. And so we see T, according to natural binary tree insertion, would belong here. And it's going to be red, my bad. And so this is kind of a problem because we said before that the red children need to be left leaning, but here we clearly see that T is the right child. And so again, this case is described as when I, being S, I'm inserting the child here, but I had no children before, and now a red node has been inserted as my right child. And so the fix-up would be to rotate left on the current node, or S. And so again, we saw rotating left means we're going to take S and make it the left child of what used to be its right child, right? We do this like rotation in this direction. And so what we end up with is T is going to be above S, and S will be red now, right? And T is going to take on the color S used to have. Sorry guys, my cable is so broken. And so this is the end result that we have, right? So this was a slightly simple case. And both of these cases, you're going to notice we're inserting onto a node that didn't have like other children already, right? Before we had done the insertion, we had just had this, right? We were inserting onto this black node that had nothing else. So now we're going to talk about more complex cases, or what happens when you insert into a node that already had children, or in other words, if you think about the analogous 2-3 tree, what happens when you're inserting into a node that already has 2 elements, right? Something like this, and you're trying to insert another one. So let's talk about that case. There's 3 different ways it can happen. In case A, let's imagine you want to insert an element like Z. And so Z would naturally go here, right? Doing binary search tree insertion, and Z is going to be red. And so here's the problem. I already have a red left child, and now I've added a red right child, right? So the problem here is that I have two red children. If you think about the analogous 2-3 tree, which looks something like this, right? We had G, V, X, Y, S, A, B, right? Inserting Z is analogous to doing this. And this is not allowed in a 2-3 tree because a 2-3 tree can only have 2 elements at most per node. And so this is the problem here. And so how can we fix this? Our solution is to color flip on the current node. And so what happens then is that we're going to end up with V, G, and then Y is now red. So actually, it's so hard to do this fast, guys. I'm trying my best. Just have to switch colors a lot. B, S, A, and now Y is red, and X and Z are black. And so that fixed the problem at this level, right? But what we're going to notice is that at the next level, the problem is repeated. But this is okay because insertion is this recursive method, right? And so we can imagine that if, let's say, at the lower levels we had recursed, right? We had started here and we had done, insert, and we had recursed down here. When we return back up to this level in our recursive call, right? When we're back up here after inserting recursively on the right, we'll just apply the same process of fixing it up. And so here at this level, we would say, oh, somehow I have 2 right children. Well, the solution here is to color flip, right? And so we would color flip again, and now we have V and then G, Y. And now we're back up at that was the very top layer, right? And so we're done recursing. And the last step is to make sure the root is always black. And so this is just sort of like a no matter what, the root is black. And so this is the end result we have. This totally works. If you were confused at any point, I recommend going back and doing that 2-3 tree insertion and seeing that it totally follows along, right? So this is the first case, case A. Case B, let's look at what happens if we insert W. And so here we see W is greater than V, but it's less than Y. W, X, yeah, the less than X2. Guys, I'm so bad at alphabet. Okay, and so W is less than X, so it would be a left child of X. But here's the problem. We're not allowed to have 2 red nodes in a row. This is one of our properties of LLRBs. And if we brought this back to our analogous 2-3 tree, again, we would have seen that this looks something like doing this, right? We're trying to insert W right here. And so that's a problem again. So how do we fix this? Well, the first thing we're going to do is rotate right on the current node, right? And so when I say current node, I'm saying X because we're imagining we're at X, or sorry. The way to fix this is to rotate right on the current node, assuming the current node is Y, and Y has observed my red left child now has a red left child of its own, or a left grandchild of mine, in other words. And so again, this is imagining we're standing at Y's viewpoint, and Y has checked. Does my red child have a red left child? If so, we should rotate right on the current node, which is Y. And so what's going to happen here is in rotate right, we do this sort of rightward rotation like this, right? And so what we end up with is V, G, A. Oh, no, that's not right. Guys, I'm going as fast as I can. X, W, Y, right? And W is also red, my bad. This is case B. And so again, we were standing here at Y's level and we had checked if I have a left child, does that left child have a left child? If both of these things are true, I have a left child and I have a left, like that left child has a left red child, I need to rotate right on myself. And so Y rotated right, and now X is the parent of Y. However, this brought us to another scenario where we have two red children, right? So in other words, when you rotate right on case B, you're gonna end up in a scenario like this. But this reduces back to case A. And so we can just do the solution we found in case A, which was to color flip, and we're gonna end up with this, right? But you're noticing again, wait. When we recurse back up to the top level, this one's gonna notice, oh crap, I have two red children, but it's okay, because this level just says, I'll fix that, I'll do a color flip. And so what we end up with is this, right? We did the color flip and this is our end result. And this totally works. Again, notice we're balanced in terms of the number of black nodes in the tree. So this is case B. When you check to see if your red child also has a red left child, like the solution is to rotate right and then go through case A. Now case C, let's imagine we're inserting B into the following tree. And so what's going to happen is B is less than V, it's less than G, it's less than C. And so we go left and it's greater than A. And so we want to make it the right child of A, right? And so now we have this problem where A notices, oh, I have a red right child. And so the way to fix this would be to rotate left on the current node, or A. And so again, what we're checking here is, do I have a red right child? If I do, I should rotate left. And so what we're going to end up with is something more like this. How y'all doing? Having a good time? I'm having so much fun. We end up with something like this, right? And so we see that by rotating right, what we did was, rotating left on A, we made A the left child of B. Notice that A was previously red, and so B took on the color of A, which was red, and so B is also still red right now. This is following the coloring rules we said during rotate left, right? This is just the way we defined it. And so now we have this chain where we have two red children. And when we go back up to C's level in our recursive tree, C is doing this check to make sure everything's good. And it's going to see, oh crap, I have a left red child, and that left red child has another left red child. And this is case B, right? We just saw how we fix this. And so again, we had been, recursively inserting. We're on our way back up doing fixes, and C notices this. And so the way it fixes this, hello, is what we just described in case B, which is to rotate right on the current node. And so C observes this and it says, okay, we're going to rotate right. And so we get B, and B should be red, sorry. Or black. And so this is what we end up with here. But then we go, oh, but remember we said after case B, what we end up with is case A. And so we have to do a color flip, right? Because B had two red children there, and that was not what we wanted. So we do a color flip, and now we have this. And we're all done here. We've fixed up case B, case A, and then we go up to the next level, and G is going to check, hey, is everything good here? And G says, oh, that's fine so far, right? And then we get up to this level, and now U or V goes, hey, I have a red left child, and my red left child has a red left child. This is case B. And so we're gonna repeat this, right? And again, we saw the way we solve this is to do a rotate right on the current node, which is V. And so V is gonna rotate right and become the child of G, and it will adopt what used to be G's child, which was S, right? And so now we have this kind of scenario. And V should become red. Oh, I just colored it black. V is red, and G took on the color that V used to be, which was black. And so this is what we end up with. And so we've just fixed case B, which means we're at case A, and so we have to color flip. You guys are probably thinking, oh God, Allison, this is so repetitive, but that's what recursion is. It's repetitive. What did I just have here? I had B, I had V, oh, and this was G, right? And now we're all done, right? And we've left, but the last step, no matter what, is to make sure the root is black. We straight up just set it to black. And so this is the end result. This is what it looks like. I just realized my picture is wrong here. It's meant to be like this. So that was complex case C. I am winded from discussing this, but you saw that it's actually pretty mechanical, and I almost just laid down some pseudocode for you in words. And so hopefully you feel prepared on how to tackle this. Some tips, hints, and hacks. Notice that case C and the slightly simple case, right, really start as the same. Both just say, rotate left when you have a red right child and a null left child. So that's the first little tip, is that case C and the slightly simple case can maybe be simplified or combined together somehow. The next thing to notice is that after fixing up case C, you're left with case B. And after fixing up case B, you're left with case A. And after fixing up case A, you're done. So does this maybe give some hints in the order in which to fix up the cases? Again, you want to avoid repeating code, right? So you don't want to write separate case B, A, C, case B, A. You know, it might be possible for you to write code in a pretty efficient manner. The next thing is just not overthink things. You are already familiar with regular old recursive binary search tree insertion. And so recall what we said is that the flow for an LLRB insertion is to do what normal BSTs do and then do the fix up. So don't overcomplicate the insertion part. You already know how to do that. The last thing is that don't forget the root should always be set to black at the end, and that's just at the very root level. And so you can consider how to make that happen. Finally, we're going to end on a disclaimer. In lecture, we've learned about both 2-3 trees and 2-4 trees, also known as 2-3-4 trees, right? And so 2-3-4 trees are B trees that can have between 1 and 3 elements per node and 2 to 4 children per node. And so a node like this is actually allowed in a 2-4 tree, right? And so LLRBs, left-leaning red-black trees, correspond to 2-3 trees, while general red-black trees, not left-leaning, correspond to 2-3-4 trees. And so red-black trees versus LLRBs, they have different rules for insertion. For example, a red-black tree is actually allowed to have a state like this, right? Because we can imagine this is analogous in the 2-3-4 tree to a node like this, and that's okay in the 2-3-4 tree. So these are totally different in terms of like the insertion rules. And so I want you to remember that throughout this homework, you're working specifically on LLRBs. I know it's done in a file called red-black tree, but it is still an LLRB that you're working on at the end of the day. There is an optional portion, not extra credit, optional portion that says like make a red-black tree, not LLRB. And that is done in the same file as all the other stuff, but that's working on a 2-4 tree. And so that's an optional part. Don't even worry about it if this is confusing to you, but basically I just wanted to make sure it's very clear what we're working on throughout this homework. We've focused on the 2-3 LLRB similarities, but be aware that this is an alternative. Both are totally valid, both work. And yeah, with that being said, have fun with homework 8. I hope you really enjoy it. Bye.